Section 3.4 Retrieving Thermodynamic Properties. To analyze a system, we'll need to determine the numerical values for the thermodynamic properties of a system. There are several ways to acquire thermodynamic properties, including the property tables, graphs, equations, and computer software. First, we'll be using the property tables. So if you look at the back of your textbook, you will find many tables. From table 8.2 to table 8.20, there are separate property tables for different substances: water, refrigerant 22, refrigerant 134A, ammonia, propane. Additionally, there are separate property tables for different phases: saturated water, superheated water vapor, compressed liquid water, saturated refrigerant, superheated refrigerant, saturated propane, and superheated propane. So we'll learn how to find the tables and read the tables. Oftentimes we'll need to do interpolations to find values in between what the tables provide. So you will need to get comfortable to use the property tables to solve thermodynamic problems. And you can also find the property tables in English unit. Section 3.5 Evaluating Pressure, Specific Volume, and Temperature. In this section, we are going to use the thermodynamic tables and determine the state of a system. First, consider a single-phase substance. We'll look at superheated vapor and compressed liquid state. Table 8.4 is the property table of superheated water vapor. Table 8.5 is the property of compressed liquid water. Let's take a look at the table. This is table 8.4, properties of superheated water vapor. The first line shows temperature, specific volumes, internal energy, enthalpy, and entropy. We'll learn about enthalpy and entropy later. So this part of the tables has the data for the pressure 0.06 bar or 0.006 megapascal. And the pressure shown here is the absolute pressure. At this pressure, saturation temperature is also shown, 36.16 degrees Celsius. What that means is that the water is in the saturated vapor state at 0.06 bar and 36.16 degrees Celsius. The first line shows here is the saturation properties. So this is the saturation properties at pressure 0.006 megapascal and saturation temperature 36.16 degrees Celsius. As the temperature increases, the state becomes superheated. So we can determine the specific heat, internal energy, enthalpy, and entropy at different temperature. The first question asks to use table 8.4 and determine the saturation temperature of water at 10 megapascal. So find the pressure 10 megapascal. So here is a 10 megapascal. And the saturation temperature at 10 megapascal is 311.06 degrees Celsius. So this is the saturation temperature. Let's see where the state is located in the property diagram. So on the PT diagram or phase diagram, there are three lines. The line indicates the two-phase mixture. So here we have solid, liquid, and vapor. And this line separates solid and vapor. This line separates solid and liquid. This line separates liquid and vapor. Table 8.4 superheated water vapor data is for this area. Superheated water vapor. Table 8.5 compressed liquid data is for this area. The three line meets at the triple points. This is called triple points, and the temperature here is 273.16 Kelvin, and the pressure here is 611.3 Pascal, and this is for water. And this is critical point. This is where the saturated liquid line and the saturated vapor line meet. At this point, the density of the liquid and gas are equal. And the pressure at the critical point is called the critical pressure. Critical pressure, which is 22.09 megapascal. And the temperature at the critical point is called critical temperature, which is 647.1 Kelvin. So in the question we had 10 megapascal and it's in the saturated vapor phase. So we expect the point is somewhere here. So this is 10 megapascal. On the TV diagram, let's say the red line is at 10 megapascal, which is constant. So this is the constant pressure line on a TV diagram. The saturated vapor is here on the saturated vapor line. So here is the critical points on the right hand side, saturated vapor line, left hand side, saturated liquid line. Next question, use table 8.4e. E here denotes English unit to determine the saturation temperature of water at 500 pounds-force per inch squared, or psi. So this is a similar questions, but we'll use the English unit. So you may pause the video and find the answer. So this is table 8.4e, and at 500 psi the saturation temperature is 467.1 degree Fahrenheit. And also the first line shows the saturation properties. The rest of the table shows the data for superheated water vapor. Determine the specific volume of water vapor at a pressure of 10 megapascal and 600 degrees Celsius. Assuming this is a simple compressible system, two independent intensive properties fix the state. So pressure and temperatures are given, so we can fix the state. That means we can determine the specific volume of water vapor. So at 10 megapascal, the saturation temperature is 311 degrees Celsius. But since the temperature 600 degrees Celsius is given, we know that the state of the system is at superheated water vapor. And the specific volume of the system, so first column, here it shows the specific volume. Specific volume at 600 degrees Celsius is 0.03837 meter cubed per kilogram. On the PT diagram, if this is 10 megapascal and this is the saturation temperature, which is 311 degrees Celsius, since the temperature in this question is 600 degrees Celsius, the points may be around here. On TV diagram, let's say this is 10 megapascal and this is the saturation temperature, 311 degrees Celsius. Temperature in this question is 600 degrees Celsius, so the state may be around this point. Now you may pause the video and solve the next question. So use table 8.4e. At pressure 500 psi and temperature 600 degree Fahrenheit, the specific volume is 1.158 feet cubed per pound. Determine the specific volume of water vapor at a state where pressure is 10 bar and temperature 215 degrees Celsius. So here is a table 8.4, and at pressure 10 bar or 1 megapascal, temperature 215 degrees Celsius. So temperature 215 sits between 200 and 240 degrees Celsius. So we need to do the linear interpolation to find the value at 215 degrees Celsius. Assume that there is a linear relationship between the temperature and the specific volumes. Y-axis is going to be temperature, x-axis going to be specific volume. At 200 degrees Celsius, specific volume is 0.2060. At 240 degrees Celsius, specific volume is 0.2275. The unit is meter cubed per kilogram. We want to determine the specific volume at 215 degrees Celsius. Let's say this is x. Assuming there is a linear relationship between the temperature and the specific volumes, we have a straight line. So we can write the slope 240 minus 200 over 0.2275 minus 0.2060. So this is the slope between these 2 points, equals slope 215 minus 200 x minus 0.2060, the slope between this point and this point. So we can solve it for x. So x is 0.2141 meter cubed per kilogram. So this is how we do the linear interpolation. This is an example in our textbook. A piston cylinder assembly containing 0.1 pounds of ammonia. Initially, a saturated vapor is placed on a hot plate. So heat is transferred to the ammonia. Due to the weight of the piston and the surrounding atmospheric pressure, the pressure of the ammonia is 20 pound-force per inch squared, or psi. So heating occurs slowly, and the ammonia expands at constant pressure until the final temperature is 77 degrees Fahrenheit. Shows the initial and final state on TV PV diagram and determine the volume occupied by the ammonia at each end state in cubic feet. Also determine the work for the process in BTU. So what is known? Ammonia is heated at constant pressure in a vertical piston cylinder assembly. So initial state is saturated vapor with a known final temperature. So let's see how we can plot the process on TV and PV diagram. So initially it was at saturated vapor state. So we know that the state should be on the saturated vapor line. So we can say initially it's at state 1 and it's on the saturated vapor line. and heat is transferred to the ammonia, and the pressure remains constant. So the process follows constant pressure line. So constant pressure lines goes up to the right, and it stops at 77 degrees Fahrenheit. This is the final state, or we call it state 2. And since it's on this side of the curve, we know that the state of the ammonia is in superheated vapor. On PV diagram, initially it's at state 1, and this is the constant temperature line. During the process, the only thing doesn't change is the pressure. So pressure remains constant, so it moves horizontally. State 2 is at the horizontal position, and the volume changes from V1 to V2. Let's write out what are knowns. At state 1, pressure is 20 psi, and it's at saturated vapor state. So we may use this table to find out the another properties. At 20 psi, the saturation temperature is negative 16.63 degrees Fahrenheit. So T1 negative 16.63 Fahrenheit. Specific volume is 13.497 cubic feet per pound. At state 2, pressure remains constant, and the temperature is given 77 degrees Fahrenheit. So two intensive independent properties are known. And we also know that it's in the superheated vapor region. So use the tables to determine the specific volume at state 2, and the specific volumes at 77 degrees Celsius. We need to interpolate the properties. V2 is calculated to be 16.7 feet cubic per pound. From the definition of specific volumes, specific volume is volume over mass. So at the initial conditions, V1 is specific volume times mass. Mass of the system doesn't change since it's a closed system. So V1 times mass and V2 is specific volume times mass. Work is this area. So work is calculated. Volume changes from V1 to V2, P times dV. Since pressure is constant, pressure times the volume change. Pressure is 20 pounds, force per inches squared, times volume change. We cannot multiply inches by feet, so use the unit conversion. and it asks us to provide the work in BTU. 1 BTU equals 778 feet-pound force. Final answer 1.18 BTU.